Okay, let's talk about transformations of graphs. Okay, in a way, I'll kind of like have this T-shirt with these different graph transformations on. Okay, I wonder if that's possible. Right? Maybe not. I don't know. I've just drawn for you 6 different but related graphs. Okay, using transformations. I'm going to talk you through the rules of these. All right, so hopefully you can just sort of see them. I'm just going to bring it a bit closer for you. So you just freeze frame it whenever you want, print it off. It's up to you how you do it. But basically, you've got to know and remember these rules for graph transformations, okay? So f of x is your standard function, and what I'm going for here is the graph y equals x squared. And you remember what the graph y equals x squared looks like, okay? So it just looks like this, of course. So a U-shaped parabola like that. Okay, it looks like a dodgy parabola at the moment because I'm just holding it up with one hand. Sorry for that. Right, that's your y equals x squared. Looking graph. So the function I'm dealing with is x squared, but these graph transformations, they apply to any graphical function at all. Okay. So when you've got f of x and then you add a number, a positive number of course, the graph gets translated upwards. Okay. If you subtract a number, so subtract 5 or subtract 7, the graph goes downwards. So the plus or minus, whatever number you have on the end, it moves the graph up or down. Okay, I'll explain that in a minute. Then this one here is a translation left or right, so f of x plus a means you move the whole graph left, f of x minus a, the whole graph gets moved right. A times f of x, where a is in front of the bracket, stretch multiplied by a in the y direction, so stretch factor a in the y direction. When the a is in the brackets, f of ax like that, so stretch 1 over a in the x direction. A bit difficult to get to grips with, okay, but I'll do my best in this video. Negative f of x, reflection of the x-axis, f of negative x, reflection of the y-axis, okay? I'm going to put those away for the moment and just look at these, okay? So as I said, this is the graph y equals x squared, and these are graphs that have been drawn under different transformations, okay? So the first transformation is when you just add a number on, okay? When you're adding a number on, all you do is just increase the y values. Okay, so this here is telling you that the y coordinates are x squared plus a. Well, if you just have that, you get the U-shaped parabola crossing through the origin. Okay, and then when you add on a value, all the y values get increased by that number, and so the whole graph gets moved upwards. The y-intercept you can see is a, so the minimum point is upwards. The minimum point is now a. That's simple, I hope. And then this, when the plus a is in the brackets, okay, it's about where the minimum point is. It's about where the minimum point is, okay? And the minimum point occurs when this bracket is 0, because 0 squared is your lowest squared value, okay? No negative values are square numbers, okay? Real numbers, don't forget. So that happens when x is negative a, okay? So negative a plus a gives you 0. So can you see, if that was like x plus 7 squared, the value of x would be negative 7. So that's why it's a shift left, okay, despite the fact it's plus a in the bracket. So just shift left. Also, when it's x minus a, okay, like x minus 5, then the value of x is positive a or positive 5, which is why the minimum point would be there, and it gets moved right, okay? And then a, x squared. Well, a bit like this one really. What's happening to the y coordinates? In this one, you're adding on a value to the y coordinates here. You're multiplying all the y coordinates by this factor. That's why it's a stretch of a factor, okay? So you're stretching it out by a factor of 2. So the graph gets stretched out by a factor of 2. That's why I try to draw it so it looks like it's stretched out compared to this one. Okay? It's still a parabolic shape, so it's still a basic shape, but I'm just trying to show you the difference between an x squared graph and when it's been stretched, okay? This one, very difficult, so I'm going to come back to it, okay? But effectively what's going on is, if you expand the brackets, you've got a squared x squared, so it still looks like it's a stretch in the y direction, but it's not, okay? It's not. At the end of this video, I'll give you demonstrations to why that's not happening. It's a stretch, a factor of 1 over a, which means it's actually stretching this way, but inwards, okay? Remember, like enlargements, okay, a large shape can be either bigger or smaller. Well, a stretch can either be stretched out or stretched inwards, okay, compressed if you prefer, okay, but the term to use is stretch, factor 1 over in the x direction, which is why it's looking a lot narrower than this graph. I'll come back to that one anyway. Here, you've got y equals negative x squared. The negative means all the y coordinates are now negative, because you square the terms first, and then you multiply by -1. So if you make all the y coordinates negative, what's happening is, if I just get this graph here as a comparison, if you make all these y coordinates negative, they end up down there, of course. So that y coordinate ends up there, that y coordinate there, that y coordinate there, that y coordinate there, and so on. So the whole graph ends up looking like this, okay? And as you should remember from your quadratic graphs, that's what a negative parabola, well, negative n-shaped parabola looks like, okay? So the transformation just reflects the whole graph through the x-axis. And lastly, it looks like nothing's happened at all, doesn't it? Because if you expand the brackets, you get y equals x squared again. So it's actually exactly the same as that graph there. This graph and that are exactly the same. But mathematically what's happening is it's been reflected about the y-axis. Okay, it's been reflected about the y-axis. That's really what's going on. Now let me just come back to a couple of those. Okay, I'm hoping that this one I'm rubbing out is quite simple. Same with this one, and with this one, and with this one. Okay, but let me just try and convince you on that about the reflection in the y-axis. So if you remember from one of the previous videos I did, the graph y equals x cubed, it looks like this. That's your traditional cubic shaped graph, like that. Okay, and then let's consider y equals negative x cubed in brackets like this. The graph of negative x cubed, when you expand the brackets, is the same as y equals negative x cubed. It's the same as that, is what I'm saying. Okay. All that means is when you've got a positive value of x, cube that, and then multiply by -1, the value of y is negative. So for all positive values of x, you get negative values of y. So what that means is that graph is going to get reflected through there and through there, and that's effectively a reflection in the y-axis. Okay. So you just couldn't see it so much from that one because the parabola is symmetrical about the y-axis anyway. This one here, you can just see it a little bit more. Okay. I want to come back to this one because this is kind of an awkward one, isn't it? The transformation y equals a f of ax. Okay, that's what I wanted to say. Transformation y equals f of ax. Okay. I'm sorry to talk about trigonometry if you weren't expecting that today, but they're best seen with trigonometric graphs. Okay, right. I'll just do sine x because that's the simplest trigonometric graph. Okay, so the graph y equals sine x. It looks something like this. All right, you should remember this from last year in GCSE. Okay, so that's 90 degrees, that's 180 degrees, it's 270 degrees, 360 degrees. Okay, just go with it for the time being. Okay, that's positive one, that's negative one. You can check these using your calculator. You just type in y equals, no, not y, type in sine 0, you get 0, sine 90, you get 1, sine 180, you get 0, sine 270, -1, sine 360, 0, okay. And you can just check all the other values if you want, but that's the important bit here. I've just jumped ahead a little bit. That's what you'll need to know in the trigonometry chapter. What if you want to draw the graph of y equals sine 2x? Okay, so that is basically this, where the a is 2. Okay. Now remember the transformation I said? It's 1 over 2 in the x direction, so it should stretch a half in the x direction, so it should stretch this way, okay, in the x direction. Well, when x is 0, y is also 0, so the crossing point is still going to be there. Okay. However, when x is 45 degrees, sine 2 times 45, sine 90 is 1. Okay, so this time when x is 45 degrees, that will give you a maximum value of 1. So can you see it's actually peaking 45 degrees earlier. Okay, and then when x is 90 degrees, sine 2 times 90 is sine 180. Sine 180 degrees is 0. So that means when x is 90 degrees, it comes back down. Okay, can you see what's happening there? So originally in the sine graph, it's going up and then down there, but in the new graph, it's going up and down in half the space. Okay, let's do the rest of the graph. So when x is 135 degrees, sine 2 times 135 is sine 270, which is -1. So 135 degrees, let's put it there, it goes down to -1. Okay, and then when x is 180 degrees, sine 2 times 180 is 360. 360 is 0, so it comes back up to 0 there. Okay, so can you see? Now, this is what we call one cycle, a period of the sine graph. Okay, that cycle is now halved. Okay, basically a sine graph is this shape continuously. Okay, this goes on forever. Okay, left and right, this goes on forever. Okay, but the repeating cycle is normally 360 degrees, so it repeats every 360 degrees. Okay, it's now halved. It now repeats every 180 degrees. So you see the compressing effect, the stretching effect this actually has, which is why I said you'd see it more on a trigonometric graph. Okay, and so that explains why that one there is a stretch of factor 1 over a in the x direction. Okay, I'm hoping that made sense for you. Remember, do revise these rules. I cannot, tell you enough just how important they actually are, because you'll need to use them again throughout the whole of year 13. Remember, in year 13 you have to do more graph sketching still, and you still have to use all of these. Okay, you should have known them from last year, okay, but you might have been out of practice. Know them for this year, okay, learn them inside out, and make sure that you remember them for next year as well. Okay, I'm hoping you found that helpful. I'm kind of pleased I got trigonometry into that, so that's good. I love trigonometry, you should too. Okay, that's it from me. Have a good day.